Welcome to composability. Ying, please tell us about the async tensor subclass we were working on.
Cool. Should I share my screen or should I
Yeah,
just
go ahead
talk?
and share your screen.
Okay. Um, this is this one. Okay. Cool. Yeah. So hi everyone. I'm on the TorchRec team, and yeah, been working with Ed on this thing called propagating async tensor, async collective tensor, and kind of the motivation is that currently the request await structure that we have in TorchRec to kind of manage overlapping, the output, the embedding all to all with dense, dense computation and like a sparse NN. Um, doesn't really work well with things like BD2. And then we've also found that customers don't really do what we ask them to do correctly a lot of the times. So kind of right now they have to write their code in very like a very rigid format. They have to call the sparse arc and then they have to call the dense arc. And then they have to call like this arbitrary function that might do like some minor post processing to their sparse output. So people get that wrong all the time. Yeah, so I think this kind of tackles both of those problems, and then I think hopefully it'll integrate well with what Will is doing with how can this thing be like reordered after like you dynamo it. Um, cool. Yeah, so I guess the basic idea is it looks. Oh, hey Will, I met welcome,
Hey.
but yeah,
Oh yeah, no. I just had a question. So,
yeah.
for those of us who kind of know what functional collectives are, but haven't been following the latest work, what's the difference between the existing async tensor and this async tensor? And is this like a replacement for it, or is this something that you have to use sometimes and not all the time?
I mean, for now, I'm just kind of hacking it in TorchRec. I guess whether like whether should be a replacement, we can decide at a
Well,
later
let me
time.
answer the question about the
Mhm.
difference. So there is currently an async tensor, which is used by the functional collective APIs. And let me describe what it does. So essentially, when you run a functional collective, you get an async tensor saying, hey, the result isn't here yet. And the first operation you run on it will wait for the collective to finish before you actually run that operation. So that's what async tensor in Torch distributed does. Propagating async tensor does something different. Actually, Ying, can you scroll down to the Torch dispatch?
Yeah. So
So what propagating async tensor does is it says, well, you're trying to run this op. Instead of waiting, I'm going to set up a callback saying, here's some work you should do later after you actually have gotten the result. And it doesn't wait. So it'll propagate the delay until some unspecified sync point. Ying, what is the sync point right now?
so right now I added a heuristic so that if a propagating tensor is interacting with a non-propagating tensor, it'll manifest there, which is that's okay for us because we don't interact with anything else. So usually like in a sparse NN it'll interact like at the first like dense sparse interaction. Because otherwise like it manifests like right before backwards, but then the CPU overhead is a bit too high for that.
Well, did that answer your question?
Yeah, I think so. Interesting. I'll stay tuned.
Cool. Yeah, I guess that's the basic idea. Implementation wise, there's like some messiness going on here, but hopefully nothing that can't be cleaned up. So then I wrote like a thin wrapper around it, and I piped this all throughout TorchRec. So this actually makes our code like a lot nicer because instead of like us manually like writing callbacks on top. Let me see if I can find it. This data. Yeah. Instead of like us managing this like callback structure that we have with like a bunch of wrappers around our own awaitable type. We just pipe the tensor through as if it's like not even distributed. Um, yeah, and then like this is another instance of where this awaitable we don't have to manage this awaitable anymore, which is pretty cool. Yeah, so I tested this out on our DLRM model, and I think it looks pretty promising. Some downsides are that because we have this 2x CPU overhead because once we record the ops and then once on manifestation, it actually runs the ops. But I think that little area of like these CPU calls should be pretty small in a larger model. And I do see in our DLRM model that we are able to get like this dense sparse overlapping because it turns out in our dense sparse model, our DLRM model right now, we don't actually use our own lazy awaitables correctly. So yeah, this kind of fixes that, which is kind of cool. Yeah, that's the basic idea. I guess some future items I'm looking at is what needs to be done to kind of fully replace, Torch Rex, Calm Ops library. I think the trickiest parts will be how does, our quantized comms interact with this, because we do some pretty naughty things, like we convert things to like uint8 to represent FP8, and then like convert that back to FP8. And like AutoGrad gave us like some issues in the past, but I'm thinking with this, the Q columns will also just be propagated, and the decoding will also be just propagated. So maybe that won't be an issue. Yeah, but still need to try that out.
Thanks. Any more questions from the room? I want to point out a few things that, Ying, thanks for the presentation. I want to point out a few more things that are sort of more from the PyTorch core side. So one of the things that TorchRec has to do to manually async things is they often have to write custom autograd functions, which sort of set up the please trigger the async call and then later please wait for it. So there's often code in TorchRec that could have been differentiated through the normal way, but instead they had to write custom autograd functions for it. So one of the things that happens with this tensor, because it is a torch dispatch tensor, is you don't have to write custom autograd functions anymore. There's a question from Alvin.
Just to clarify, is that something that we could use hooks for, or can you give a little bit more detail?
Yeah. Well, Ying, I don't know if you have this handy in your diff or not. We can swap screens otherwise if you want.
Hooks for
So we're specifically talking about the rec and the wait autograd functions in column ops.
Oh, yes. So these guys.
Yeah.
Like
Except
I guess
it's not
I
here
guess like,
because we've got to expand the diff a little. Yeah.
like currently or like in the idea.
Yeah. So let's look at the before and let's look at the after.
Sorry, this I don't know how to expand this. All the way down.
Why don't you just
Wait,
click go up here and then click view file. Yeah. And then you can just skip to
info. Yeah, so like something like this right now. But right now this will not be used.
So Albin, so this is what they're currently using an autograd function for. And so what's going on here is that so this is the wait function. So this gets called after you've already triggered the async request. And all it says is, okay, given the input async request my rec, wait on it, and then do some operations on it. And then the backwards does the sort of reverse, which is it performs the collective and then squirrels away this async thing on the myrec object, so that there's another autograd function whose backward then knows to wait on it later. Yeah, the one Ying has done here. So I don't know. It doesn't seem like you can do it with hooks. But also, once you have propagating async tensor, you don't need these autograd functions anymore. You just write the forward code and differentiate through it the normal way.
Here's like a visual. If folks like this is like the visual of what we currently do, to try to like manage this like async kind of thing.
Did that
Yeah,
answer
makes
your
sense.
question, Alvin?
Yes, thank you.
Okay. So another thing that I want to point out is that there are some problems with tensor subclasses that Ying had to work around. So let me think. Can you pop to your tensor subclass implementation? I just want to look at it a little bit.
Yeah.
Actually, can you just walk us through some of the like weird problems you ran into while working on this?
Yeah, so basically all these stubs, like split, reshape, view, narrow, transpose. To be honest, I don't know what these things have in common that Torch Dispatch doesn't like. I just get
They're
those
all
angry.
views. That's why Torch Dispatch doesn't like them.
Okay. Yeah, so I got this angry message, couldn't spend some time, couldn't get around it, so just monkey patch these for now. But ideally, these all just are done in the functional dispatch that can generalize. But yeah.
Let me think. Another thing that I want to remark is we kind of wanted to use fake tensor. So when you do this propagating async tensor, you have a problem, which is that because it's a tensor subclass, you need to know what the size and D type, everything about the resulting tensor is, even though you haven't actually run the callback. So we're currently using a meta tensor to do this because fake tensor is too slow because, well, everyone knows fake tensor is slow. But you have to run the meta operation first, and then you run the real operation later when you hit the callback. That's the 2x CPU overhead at minimum problem.
Ed, do you think on that end, with fake tensor being heavily, or like potentially a blocker, or like a significant cut in the dynamo compile time, and if we have other usage, do you think there is some space for us to investigate how we could redesign the implementation of it to make it more efficient?
Well, I don't want to write the metas in C++, like all the metas in C++. So that's sort of like, for me, the biggest problem. I don't really know how to deal with that. For
So
like the torch-rec use case, these propagating regions don't last too long. So it's like not unreasonable to say we'll just C++ metaify the like 10 ops that you're actually going to hit during the like propagating segment. But if you want to propagate arbitrarily far, it does seem like trouble.
I'm confused here. You are, even in this version that uses meta tensor, you are using the meta implementations in Python. So my understanding was only the fake tensor layer on top of it is slow, not the meta implementations.
Ying, you did the benchmarks, but you said it was only 2x CPU overhead, right?
Yeah.
So I would
tensor.
guess that you Albin, that they are actually hitting the C++ metas, because we do have C++ metas for many of these view operations.
Oh yeah, we do. No, but hence my question, like, do you think the fake tensor layer is one that we should investigate where, these kind of things would be, as you said, a lot
Well, I
easier
mean, we
to
know
do?
why it is slow. It's slow because it's written in Python, and it's slow because the decomps do tons of recursive
Yes.
function calls to decompose.
Let's see decomps. Okay.
So like it could be that like maybe we need to figure out how to like have some caching system on fake tensor prop so that that's not a problem. But yeah, that's just not so easy to like understand how it would actually work.
What's the issue with using meta tensors today to do this? Is it just like kind of not the right thing to do? It's kind of
No. Meta is fine. But Alvin is like, oh, fake tensors shouldn't be slow, which I agree. Like, fake tensors being slow is a big pain.
I think the 1,000-mile high mental model I have is fake tensor is a meta tensor with the device also correct. So if you use meta tensor, your device is going to be meta instead of whatever it was supposed to be.
Oh yeah, I do some hacks here. I do some tricks here to like get the device propagating correctly, which is
and the device propagation is pretty easy, right? So it shouldn't be a major blocker for you. So I don't think there's an issue with you using meta here. But
okay.
It's more on principle. Could we get that for you?
Gotcha.
Okay. I think that's everything I wanted to add. Are there any more questions that popped up? Okay, I'm going to call on some people. Will, Feng, does this interact with your thing at all?
Uh, to some extent, I look at Ying's work as eager mode async tensor without scheduler. Um, so my work is mainly looking at compile, and then the unit of work, instead of being a per op level, it's like I want it to be per FX graph level, and then with a scheduler. So I can see a future when like Ying's work landed, and then we can connect a scheduler to this, and then it will also be able to schedule eager ops following a static schedule. So it's like complementary, I think.
Actually, speaking of a schedule, Ying, let's say that I have some branching computation where I have a propagating async tensor that gets used by two independent expressions, and then let's say that I sync on one of them, the other one won't get synced. Is that right? It'll only get synced when I actually use it. Is that right?
Sync like manifested, like the
Manifested,
ops get
yeah.
run. I think because they funked everything, it should be like the only like you only have to run the repeated ops like on the things that differ.
Right. So you don't have to repeat, but you so the thing that might be something we should like probably fix at some point is right now your heuristic is if you have a dense tensor manifest so that you never are holding on to dense tensors longer than you should in the chain of propagating operations. But if you manifest a thunk, uh, then another thunk, which hasn't been manifested, which references that thunk, can now keep it live for too long. Does that make sense?
Is that more of like a memory
It has
issue?
a
Like,
memory thing. It's
okay,
like if you manifest, you probably want to manifest all the thunks, not just the ones that are reachable.
oh, gotcha. Yeah, I guess I was also thinking like there's no way for the all to all to actually trigger something when it finishes, right? Because like right now that we only
Yeah, that's
run
also
the
why I was asking Will Feng if that was related, because it would be nice to just start manifesting as soon as the all to all was done.
right. Um, yeah, I get just yeah. Right now they'll hold on to both of it until
But in fact, Will, we had this conversation with the polling version of your scheduler, and wasn't the conclusion of the room that it is impossible to have an arbitrary Python callback trigger as soon as some communication is done? Is that right?
Yes, I think so. I mean, yeah, I don't think that's possible right now. Like, I mean, we will need some like CUDA API at least to like be able to like call back from the CUDA region to the Python region, which we don't have anything like that right now.
Yeah, I don't think that's a thing. But okay, Ying, now I'm wondering, why don't we use implicit pipelining here? If we put these tensor operations on the communication stream, wouldn't that also work?
I think so. So like still use this, run everything on a separate stream, and then when things get manifested.
And then we don't need the lambdas. So the propagating tensor is just for ensuring we do the wait when we want to manifest. But we're just using implicit pipelining rather than explicit callbacks.
But how do these ops know when to get run?
Uh, they don't. They're just put on the communication stream, so they don't actually run until the comms are done. It's like
But
implicit,
I guess
yeah, implicit pipelining.
oh, like we just kick it off, then we just call
We
wait.
just kick it off, but because it's on the correct stream, it will wait.
So it'll be like start the all to wall, wait on the wall to wall, and then run these ops. On
You know,
on
you
that
don't
stream.
you don't want to do a wait because, well,
Yeah, I think you do actually. It's the wait is just going to make the kernel get launched. for CUDA.
Like you want one of these ops on like that on that bit of memory that's not actually a final all-to-all result, right?
But the nickel call should block the stream until the memory is properly populated. So if you enqueue on the same stream, your op will have to wait until the nickel call is done, basically.
Oh, okay.
And that's why Head was mentioning implicit pipelining. It's not explicit where you say wait and then run something else, and you move your code around so that they overlap. Here we rely on the fact that the CUDA API is naturally asynchronous, and and you can shove a bunch of job and the GPU will do it based on that.
Oh, okay, I see.
Why didn't we do this? Ying, this is my fault. I like just went straight to the Lambda.
I left the comment. I left the comment on the original doc saying why couldn't we use streams? But then I convinced myself that we had to use call this wait. So then
No, but I'm not convinced. Convince me, or have you been unconvinced?
I accidentally convinced myself incorrectly, maybe.
Yeah, so maybe we can do a version of this with streams. That would be nice.
I'll give that a try.
Yeah, that would be nice.
Oh, and I would say from what we did with Andrew on FSDP, like getting any kind of CPU synchronization out of the window is very beneficial, because anything that happens on the CPU introduce non-determinism, because depending on how far ahead your GPU is, the synchronization can happen in very different orders, and things can or cannot overlap in a pretty unknown way.
Okay, but to be clear, we're not actually synchronizing here. Like when I say, actually, are we synchronizing, Ying? Do you know?
Synchronizing which
when you manifest, you don't actually wait, right?
Well, it calls wait first and then runs all the ops.
Event wait or what?
Wait on the functional collective thing.
Okay, Will Constable has his hands raised. Will, can you answer? Does the wait on the functional collective, does that actually do a CPU wait, or is it just setting up an event? And then ask your question.
The functional collective wait is going to call it. That's actually calling the work.wait, which I think synchronizes the side stream from the collective back to the mainstream, which would be I think CPU side sync.
It depends on which of the APIs you use, but no, if you sync stream to stream, that's not CPU, so that's good.
Yeah, you're right. There's no CUDA synchronize here. You're just synchronizing the side stream back to the mainstream when you do this.
If you do event wait, it will be a CPU sync as well. You need really an explicit stream to stream wait to not have that issue.
I think what really does here is just like the work.wait do this CUDA waiting event, something like that. It's just like a stream to stream thing. There's no CPU there, if I understand correctly.
Yeah, all these APIs are very subtle, so we would need to look at exactly which API you're calling from CUDA to answer that question.
Okay, but then to answer the question of like what's the difference between this and the implicit prefetching, I guess the answer is that with implicit prefetching, you would immediately queue things on the com stream. But with what we have right now, what's going on is we delay queuing the kernels until some later point in time, and we put the kernels on the mainstream instead of the com stream. We insert the wait between the two strings later in time. And so whether or not this is go ahead.
The issue with like this implicit pipeline thing is that user code will have to do something to synchronize these, right?
No. So you just you sync back from the com stream to the mainstream at the same time you were doing the wait you were doing here.
I synchronize.
Is that true?
I see.
I guess there's also
wait, but not all the ops afterwards won't be like.
You got to make sure all the ops afterwards get synced as well. So yeah, it's a little tricky. Well,
I just wanted to ask about Torch compile, because I'm thinking about, you mentioned in FSDP case we were able to just use streams, and I think the way we're doing that is that we're kind of ignoring the streams when we're tracing, and then we're assuming the compiler is going to take care of the prefetching and making sure they happen at the right time. So we're not really capturing the intended synchronization or ordering from user stream usage. And if that might be a difference for your case.
That's actually fine because that was our plan for this as well, which is when we're tracing, we just don't do the propagating async tensor. We just give you we wait and give you the real tensor.
Okay.
Albin?
Yeah, no, my final comment was just that if we want to look at the only using stream option, we should look at it offline, I think.
Yeah, that's fine. We don't have to design it here. I just want to remark that I guess the one reason why it might be profitable to delay is if you're doing a will-fung style scheduler thing where you do want to reorder the ops after you see a bunch of them. Because once you issue them to the CUDA stream, they're just going to run in that order. You don't have any option. So I guess if you don't want to do that, then it's probably better to like do the streaming based version.
Wait, streaming based is easier with Will's thing?
No. I'm saying that you have the option to like reorder operations with the callbacks and manifestation as you've done it here.
Right.
You don't have that option if you are immediately issuing to the com stream.
Gotcha. I'll prototype it out. See what happens.
Okay,
Just
sounds cool. Okay. Thanks everyone. Let me see. Let's roll this into Will Feng's thing. Will, do you want to present your doc?
Sure. Yeah. Can you all see it?
Yes, I can see it.
Okay, thanks. Yeah, it's a pretty long doc. But I think it's a good segue from Ying's work. So Ying's work, if I were to describe it, is like eager mode async tensor without a scheduler, and then and doing async at like a per op level. So my work is doing async at the per fx graph level and with a scheduler. So particularly like the unit of work right now is like each fx graph is instead of each op, and the scheduler is like kind of a static schedule that user provide, specifying in which order those fx graphs should run, and then when we at runtime we just like faithfully follow the schedule to run those fx graphs in the right order. So particularly, I believe for like so generally like if a model have like exposed like long communication region and there are other parts of compute that don't depend on this communication, then it would help the using this like cross graph overlap will likely help. For example, like for internal models, we can like delay the gradient compute or reduce and optimize update for some overarch ways to the next iteration. And for example, like prefetching input sparse feature data, or like doing the sparse and dense overlap, like this kind of thing can all benefit from having a scheduler. Yeah. In terms of how we do it, so yeah, it's just a bunch of text here. I can just like verbally describe it. Maybe here's better. Like during compile time, we will the dynamo will follow the user provided schedule to extract out the fx graph for each concept. There is one for segment, which is like which is how users specify like a segment is like a bunch of like Python functions. So within each Python function, there will be like multiple fx graphs, and then users specify how each segment should overlap with other segment. So during the compile time, user provide a schedule of segments, and then Dynamo will follow the schedule and then slice the graph if necessary. And then Dynamo will also send a list of the FX graph of each segment to a scheduler for store for later use. So lots. Yeah.
I have a super quick question. Do
Yeah.
you mind if I interrupt here?
Go ahead. Yeah.
How does Dynamo follow the schedule? Is it just like eager code running that then Dynamo respects the bytecode for? Or does Dynamo actually know about the object in some way and does the reordering itself?
Yeah, it's a good question. I think either approach can work. I haven't like thought through like exactly which direction to go, but I think either approach can work. Yeah.
It strongly to me feels like you should just do it in eager and then pass it over to Dynamo and then like let Dynamo respect it as if you had authored it in that order. I don't know if folks have other thoughts.
Yeah, I think it would be nice if it's like a eager mode API and then we just like let Dynamo understand it. Like it makes sense. Yeah. Cool. Yeah. So I might just continue. At compile time, inductor would do the fusion and intrograph reordering within each FX graph. So this is like it's like current behavior. So nothing is changing. At runtime, for each graph, when we are at the inductor graph entry point, so remember that we detach the graph recording and the graph scheduling. So we first will record the FX graph, and it's like input arguments to get the execution handle and build up this like FX graph to handle kind of mapping. And then we check the FX graph against the schedule. We will first try to schedule all the graphs before this graph in the schedule. And if all the preceding graph are scheduled, then we schedule this graph. When we schedule, we don't wait on it. We immediately just return the async tensor, and then the async tensor will be propagated downstream to all of the subsequent graphs. So people I think there's like a important question to ask, which is that like if we hit a graph break after FS graph and we need the value of the tensor immediately, how do we get those values? So we can do that because so when we hit the eager mode region, and then eager mode calls any operations on the async tensor itself, we will actually wait on the we'll actually immediately issue the execution of the XX graph and then wait on the result of it. So in that way, eager region will always get the right the correct tensor value.
Will, do you have an example below, or?
Yeah. Let me see. Yeah, I mean, I have like kind of walkthrough of like kind of execution steps. Yeah. So here, assuming the eager mode execution order of graphs is like 0, 1, 2, 3, 4, and then the user provided schedule is like 1, 0, 2, 3, 4. So at runtime, when we first hit the graph 0, we'll first record the handle for graph 0, and then we check the schedule and find, oh, the next graph in the schedule is actually not 0. So we just like return we'll just return the async tensor. And then we move on to the next graph. At the graph 1, we first record the handle for graph 1, and then we find the next graph in schedule is 1. So we execute 1 and then move the pointer in the schedule. And then for 2, we find that there's a 0 in front of 2, which is already executable. So we execute it, and then we will also execute 2 and then move the pointer. So that's like kind of how we check against the schedule and schedule everything before the current graph that's schedulable.
Okay, Voss?
Voss?
Yeah. So super quick question. I guess we talked about segments, and I think that made sense. But on graphs, what is a graph? Like, is it if I have a graph break in something, I now have two graphs? Is it just to that level of granularity? Is this like PT2 graphs we're already lowering?
Yeah, that's right.
So then what I worry about is you have this intersection of model design at this point in time and PT2 graph breaks in this point in time that enshrine what goes in your schedule. If I fix a graph break in PT2 tomorrow, and now my schedule has like 6 numbers in it, but now after I fix a graph break, there's only 2 graphs. What does that mean for my schedule? And imagine I fix all the graph breaks in your model. Now there is nothing to reschedule.
Yeah, that's a good question. So the schedule itself is actually higher level than the graph, because like segments are like collections of graphs, like, and I don't specify how many graphs I have in each segment. I just
So to
specify.
be clear, well, you're
Yeah.
defining segments as being literal functions. Is that right?
Yeah, literal Python function names.
This I see. That still feels like we're enshrining a specific state. Because you're not like I sort of thought you would first do analysis, pull out all the collectives or find like all the leaves, and then operate on that. Operating on the raw Python, I guess, makes sense. But then if I change the name of a function, it feels like a pretty big action at a distance to then figure out that I have to go and change some schedule somewhere. Especially in a prod model, I imagine these schedules are going to live pretty far away from where the models are defined, right?
Yeah, I look at it as kind of like a user thing. I mean, I want them to have them live together, like, because it maps to Python names, so if they should have them together.
So,
Yeah,
well, let me try to describe what this system is a little differently. So, in FX land, we had this concept where people like ingest their model and then they just do some model specific surgery, just moving stuff around. And for reasons, they wanted that surgery part to be factored separately from the actual model itself. So that's kind of what's going on here, right? You're saying, well, I've got a model, it has a bunch of, things it calls, and I want to be able to say, oh, I want them to run in this other order, and I want the schedule to be separate from the, semantics of the model, and then just have some system that can actually reorder the model in this case. And the particular implementation mechanism here is this scheduler thing that waits until it sees things later. But for example, in Voz's example, what if you captured everything? Well, if you captured everything, then you could potentially just have it be a graph transform that moves things around. And that would also be a acceptable implementation.
Yeah, I think so. So I think for graph transform use cases, I think for Piper right now, we do kind of have everything in FX first and then decide how to transform the model. Like for this use case, we probably have a different API for people to group together different FX graphs together. I think it will be different from the proposal here is more targeting towards HPC trainer or APS style where people don't have a graph transform stack in between.
Voz, any follow-up questions?
Yeah, I mean, I'm still not sold that doing this by string matching is the right way to do it, but the rest of it makes sense with segments and reordering and stuff. I do just wonder if there's a better way to say this is like a thing I am moving around.
Wanchao?
So yeah, I think the graph part looks reasonable. I was just thinking that I think after our face-to-face discussion, I thought at least me, I was more interested in the how we do this prefetching in the eager mode without uh graph at all, and then torch compile comes in just to compile the schedules. And I'm wondering if we have thought about this too.
Yeah, so this theoretically can work in eager mode. It's I think in eager mode, the concern will be on what's the unit of work that we schedule. Like, is it on a per op level or like per Python function level or somewhere in between? So because per op level is certainly flexible, and then like we can have it work maybe through just dispatch mode, which is like transparent to the user, but per op overhead will also be high. So so that might be a concern.
Alvin?
Yeah, I wanted to go back a little bit to what Will was saying. Is one of the high-level description of what you're doing here is, with respect to the graph break, is you actually trying to have a high-level concept that would, in spirit, enforce a graph break at the boundary of these functions so that you have access to them as a single graph, and then you can manipulate them. What is wrong with that view?
Sorry, what was the question?
So the question is, Woz was asking, like, how does this interact with graph break, and how, Dynamo is a very dynamic system. Is my understanding here that you're trying to build a higher level system above Dynamo that will try to tell Dynamo, this is where you're going to have to graph break. These are the kind of pieces you will have to consider in a more instructive way so that you have something more stable than what we would have today otherwise.
I think so. So like the schedule tells the Dynamo where we must slice the graph, but it doesn't tell Dynamo about anything else. Like Dynamo can decide where else graph break should happen or not, but just at a segment boundary where we must have graph break.
Sounds good. Okay.
I want to return to Wan Chao's question for a moment. Also, sorry, Sam, we may not actually get to yours today.
No problem.
So Wan Chao said he was mostly interested in how we are going to do prefetching in eager. And we just spent the first half of composability talking about this propagating async tensor, which, well, actually, so let's just, given the result of the discussion, the way the propagating async tensor works is it is basically a way to more conveniently shunt tensor operations to side streams so that you can keep going on the main thread without waiting for communication to happen. So what if I just said, Wan Chao, for eager, we should just use Ying's thing? Like, would that be satisfying, or what makes you feel not good about that?
Sorry, I haven't looked too much into Yinxing, but I thought it's very similar to our async collective tensor, where you have to call, for example, auto single somewhere first, and then propagate the async collective tensor. And then the thing that I think we need for us to write an easy version of data parallel or fault-sharded data parallel is that there's a way for us to have a schedule and determine where we do prefetch, like where we actually call the collective beforehand, right? Like, would ins work? Help on that?
Well, okay, so Ying, you're still here, right? Can you tell us a little bit about how TorchRec makes sure it actually calls the collectives, like, or as early as possible?
Well, I guess for TorchRec, it's easier for us because we're not prefetching weights. Like, because since we're just calling all tool on the outputs like this, like a TVE, we just call TVE and then just feed that through the all tool. So I guess it's not really a prefetching thing happening with us.
Okay, so I guess then, okay, it doesn't transfer. That's too bad. Okay, so you're saying with TorchRec, it's the place where the prefetch happens is very logical and where you would normally put it, but that's not the case for Wan Chao stuff. Okay, so now Wan Chao and Will Feng, let me ask you. So Will, how would your thing ensure that the prefetch happens early? Because in fact, it doesn't seem like the prefetch will happen for early, right? Like, given your example, I would have to get the CPU thread to the point where I fetch the weights for the weights to actually get fetched. And all really that I'm getting saved is that I didn't queue up graph 0. If you go back to your, little example, if graph 1 is the weight fetch and graph 0 is some, doesn't need weight computation, right? I still have to actually get to 1 on CPU before I can run it.
Yeah, that's true. I'm expecting one, like the action of scheduling to happen very fast. Like we go through the whole model and then like the CPU runs much ahead at here, like so that we can hit like 1 very soon.
Wenchao, do you believe that?
I'm not quite convinced in terms like CPU is much faster.
Will Constable?
Yeah.
So I don't think it's really even about how fast you go ahead, because for FSDP, it's not really an ordering thing. It's a memory thing. Like the order is the easy part for FSDP. We can just do it in the same order as we issued them in, but we want to start them as early as possible, constrained by some memory usage. I don't really see how the scheduler system even solves that.
So
Go ahead.
So I think it's a static schedule. So right now it's like fully user specified, but on top of that, we might be able to like make it smarter in terms of like generating a schedule considering memory.
Oh, so are you saying that in this schedule in particular, user sort of at this moment you're proposing that the user sort of write a schedule and this schedule already determine where to prefetch, and then like then this schedule just get faithfully executed. Is it what this
That's
proposal?
right.
I see.
Yeah.
No. Sorry, I don't think that's what Wilfeng is proposing. I think Wilfeng's schedule is the user tells the order in which to run things, but not where to run them, which is a key difference. Like Wanchao's version is that maybe the user says like, please run layer 2s all together before layer 1 or something, and that's their version of hinting. But that's not what Wilfeng's proposal looks like to me.
But Will, what you said is ordering, right?
Well, it's ordering like relative to things that aren't in the schedule, I guess. So let's say we have 10 allgathers. So there's like 10 segments and we want to run them in order. So we're going to run 0, 1, 2, 3, 4, etc. But then we need to have some other list of non-allgathers and say that, okay, we want to run the allgather 0 before like some function. So I guess actually you could break the program down into segments where you have a compute segment and a communication segment and a compute segment. And then you could manually specify the ordering of those. And that would solve it. I didn't think about it that way before.
Yeah. I think that could solve it, maybe.
Wait, now I'm kind of curious what happens if you do want to define something as running only when something else finishes and not like in a perfectly strict order. Like, oh, I don't care if 2 or 3 are swapped, but I have to have like 3 after 0, for example. And I want to run it as soon as 0 finishes. Is that a thing, or will you always end up like just waiting for these things that we didn't have to wait for?
I think it's just maybe just a version of the schedule. Like it can be different versions that all are valid, and the user might just need to be opinionated about which version to run.
I guess what I mean is there a world where like the most optimal thing isn't as to go 1, 0, 2, 3, 4. It's to say 3 runs when 0 is done and 2 runs when 1 is done, for example. I think that's what Will Constable is asking, right? Is like, is there a way to declare dependencies?
I think there are some constraints about declaring dependencies that if we have like, let's say if we have compute node and communication node layout in segments, And it seems to me that these are like hard-coded dependency, and you can only move your communication beforehand unless you have a like sort of a graph to encode the dependency. Yeah, I'm actually not sure how this could be done.
So okay, let me riff off of Ying's thing for a little bit. So if I wanted to okay, let's imagine that I can somehow run the CPU ahead, right? So this is going to look a lot like lazy tensor, right? Which is I run the CPU ahead far enough so that I like see all the stuff that I'm eventually going to end up executing. And let's say that there's some way for me to identify which ops are in what segments. So Will has proposed functions. I'm not sure functions are enough, but let's say that somehow you're able to do this, right? So then all the scheduler needs to do is issue, the operations on the appropriate streams in the appropriate orders with correct synchronizations. But it actually has all the information it needs because in lazy tensor style, it has waited until it has gotten all the info before it goes ahead and does things. So like, I don't know what the performance characteristics of the system will be, but it certainly feels like it would be possible to make functionally correct. Alvin?
I'm slightly curious with that mental model, as in, if you know everything if you have control over that code, why can't you, quote unquote, just use implicit prefetching? And, as you discover these operations and queue them in the streams.
Well, but Alvin, this is the discussion we were having on Ying's thing, right? Which is that the implicit prefetching can be done as you go, as long as you know what order you're going to run things in, right? The moment you are like, actually, I need to run this thing before this other thing, right? You have to wait. You have to delay like actually putting things on the queue, because once you put things on the queue for a stream, that's it, right? The no take backsies.
Okay. I'm wondering how if that conflicts with the CPU is far ahead enough.
Well, yeah. So the performance thing is a bit trouble, and you also don't want to wait until you get all the way to the end because XLA did that, and we know it's a bad idea. Will, go ahead.
I wanted to ask how graph breaks work because I think I missed that part. So if you have a segment that's like my function, and then somewhere in the middle there's a graph break, so it's really going to turn into two graphs and a eager section. So then you want the scheduler to make my function run sometime later. So what does this mean? Like, does Dynamo see the beginning of my function and then just not do anything until later? Or does Dynamo actually start going into it and will the graph break part like run now?
Let me try to answer this. So in my opinion, if you believe the system works for eager mode, you should also believe it works for graph breaks.
Yeah, the scheduler doesn't see into it. So there are some assumption here. So like we assume we're not like recompiling. I mean, sorry, how should I say it? So it works through a recompile as well because it doesn't schedule at the graph. Like it look at the schedule at the segment level, not the graph level.
I guess the point is, if your Python function has no side effect and can be reordered, then it's fine.
Yeah, and we assume that for the compiled region, I think.
No, you can have side effects.
Yeah, it's okay to reorder even with side effects, right? Because you're only reordering the CUDA device compute. Go ahead, Voss.
I was gonna say, you're gonna reorder to Will's point, if you have a graph break in a segment, let's say there's like a whole segment that has like a graph break entirely within it. So there's a graph entirely within a segment. So you enter a segment, You compute something out of it, you graph break, you enter, you compute a few more ops into the whole graph, you break again, and then the return for your segment is in there. So now you have a graph that's wholly within a segment, and then that has some side effects. How do you reorder that?
Let me try to answer that. So, so let's say that I've defined my segment to be this function, which has the graph break in it. So what I will do is I will treat both subgraphs in the function call as being part of the same segment. And I will, yeah. So I'll just like shove it in, and the schedule will be like, okay, this is part of segment 2. And then I'll shove in something else, and that'll also be part of segment 2. So I'm going to have a concept where I can push multiple things to the scheduler that all get put in the same segment.
I see. So you're basically making like a higher level function that may then call like a bunch of other things under the hood, some of which are compiled functions.
Yeah.
Okay, that seems reasonable.
And there's some like dependency analysis, because like I have to make sure I don't violate dependencies. But like, yeah, I mean that's like is expected. Okay, we are out of time for the meeting. Wolfgang, it does seem like there is a bit of confusion and also a bit of like, I wouldn't call it bike shedding, but like, unresolved design questions. What do you think the right follow-up here is?
Yeah, I think I want to discuss with Wang Chao and Will on like the cases that they brought up. And I think it will also be beneficial for me to like make it maybe into a prototype and get it running on DRM to like show the benefit and also like really discuss on particular design
but hang on, but
decisions.
DLRM is easy. Well, Ying told us DLRM is easy because you just run the all to all right when you're ready.
But that's the case with all torch models, I guess. I guess the complicated part is just like it's slightly bigger.
Yeah.
Your
So the
local
questions we were getting were stuff like FSDP, where we're doing the parameter fetch instead.
Yeah, I think prototyping for FSDP would be valuable. And yeah, and also to prove the like cross iteration kind of things, I can like maybe beef up the DRM model to make it like harder so that we can show the benefit. I mean, that would also better represent the production models maybe.
To be clear, TorchRec DLRM uses train pipeline. Is that correct, Ying? Which I think does do some cross iteration stuff.
I don't know. Yes, I like the main training script uses it, but I think like for all other
Yeah,
tests
that's
as well.
right. Yeah.
Yeah. I guess
right.
like that's
Yeah.
torch one of fetching, but we do it very hackily. But yeah.
Okay. So I'm going to let everyone go. Thanks everyone for a wonderful discussion. See you all next week.
Thank you.